There is a paradox at the very heart of modern physics that has baffled both scientists and cosmos enthusiasts for decades. It is a puzzle that challenges the very foundation of how we perceive the universe around us. If black holes are so massive that not even light, traveling at 300 million meters per second, can escape their gravitational pull, then a disturbing question arises. How is it possible that we feel their gravitational influence from the outside? How can gravity escape from a cosmic prison from which not even light can break free? Tonight on Nocturnal Science, we will unravel one of the most elegant mysteries of the universe. We will embark on a journey that bridges the gap between human intuition and the extreme realities of deep space. A paradox that will take us from the curvature of spacetime to the gravitational waves detected by LIGO, revealing a truth about the nature of reality that will forever change your understanding of gravity. If you find it fascinating to explore the deepest enigmas of the cosmos while immersing yourself in nocturnal tranquility, I invite you to join us. Step into this journey where every discovery illuminates the hidden architecture of the universe. What if I told you that for decades we have been asking the wrong question about one of the most mysterious objects in the universe? And that this incorrect question has hidden a fundamental truth about the very nature of reality. Black holes have captured our imagination precisely because they seem to violate our most basic intuitions about cause and effect. They stand as silent sentinels at the edge of comprehension, creating a paradox that defies logic itself. Imagine for a moment that you are standing on the edge of a cosmic precipice, contemplating a black hole from a safe distance. The sheer scale of the darkness before you is both terrifying and profoundly beautiful. From your perspective, this invisible object exerts such a powerful gravitational influence that it can keep entire stars orbiting around it at breakneck speeds. You can observe how matter accelerates towards it, tearing apart violently as it falls. You see how it heats up to incredible temperatures, forming a blindingly bright accretion disk. It emits intense radiation, screaming into the void before disappearing forever beyond the event horizon. The implications of something being able to exert gravitational influence without allowing anything to escape raise fundamental questions. These questions strike at the heart of causality, information, and the very nature of physical forces. If we accept that nothing can travel faster than light and simultaneously observe that light cannot escape a black hole, a crisis of physics emerges. The very existence of external gravitational effects seems to violate the most basic principles we hold dear. This paradox threatens our coherent understanding of the cosmos, threatening to unravel the tapestry of modern science. For generations, scientists and philosophers have wrestled with this apparent contradiction in the dark. If gravity needed to travel from the inside of the black hole to the outside to exert its influence, it would face an insurmountable barrier. It should be subject to the exact same limitations that prevent light from escaping. But clearly, looking at the celestial mechanics around us, this is not what we observe. Black holes exert undeniable gravitational attraction, maintain perfectly stable orbits, and actively participate in the cosmic dance of galaxies. The paradox becomes even more baffling when we consider the practical implications for modern astronomy. Astronomers can detect these dark behemoths precisely through their gravitational effects on nearby objects. We observe stars orbiting invisible companions, accelerating to speeds that can only be explained by the presence of extremely massive and compact objects. If gravity could not escape these objects, they would be completely undetectable and irrelevant to the rest of the universe. They would be ghosts, having no physical tether to the galaxies they inhabit. But this is where our perspective begins to fundamentally change, revealing that the paradox itself is an illusion. It is based on an incomplete and somewhat archaic understanding of what gravity really is. For centuries, we have thought of gravity as a force that acts at a distance, a rigid tether between masses. We imagined it as something that massive objects actively send through space to influence other objects. This Newtonian perspective, while extraordinarily useful for building bridges and launching rockets, has severe limits. It has led us to ask questions that contain incorrect assumptions about the fundamental nature of gravitation. The core question, how does gravity escape? It presupposes that gravity is an entity that needs to escape from somewhere. It assumes that gravity is a signal that originates inside the black hole and must travel outward to exert its influence. This assumption is deeply rooted in our everyday terrestrial intuition about forces and effects, and it is precisely this flawed human intuition that creates the apparent paradox. Let's consider a simple analogy that begins to illuminate the resolution to this cosmic riddle. There is a paradox at the very heart of modern physics that has baffled both scientists and cosmos enthusiasts for decades. It is a puzzle that challenges the very foundation of how we perceive the universe around us. If black holes are so massive that not even light, traveling at 300 million meters per second, can escape their gravitational pull, then a disturbing question arises. How is it possible that we feel their gravitational influence from the outside? How can gravity escape from a cosmic prison from which not even light can break free? Tonight on Nocturnal Science, we will unravel one of the most elegant mysteries of the universe. We will embark on a journey that bridges the gap between human intuition and the extreme realities of deep space. A paradox that will take us from the curvature of spacetime to the gravitational waves detected by LIGO, revealing a truth about the nature of reality that will forever change your understanding of gravity. If you find it fascinating to explore the deepest enigmas of the cosmos while immersing yourself in nocturnal tranquility, I invite you to join us. Step into this journey where every discovery illuminates the hidden architecture of the universe. What if I told you that for decades we have been asking the wrong question about one of the most mysterious objects in the universe? And that this incorrect question has hidden a fundamental truth about the very nature of reality? Black holes have captured our imagination precisely because they seem to violate our most basic intuitions about cause and effect. They stand as silent sentinels at the edge of comprehension, creating a paradox that defies logic itself. Imagine for a moment that you are standing on the edge of a cosmic precipice, contemplating a black hole from a safe distance. The sheer scale of the darkness before you is both terrifying and profoundly beautiful. From your perspective, this invisible object exerts such a powerful gravitational influence that it can keep entire stars orbiting around it at breakneck speeds. You can observe how matter accelerates towards it, tearing apart violently as it falls. You see how it heats up to incredible temperatures, forming a blindingly bright accretion disk. It emits intense radiation, screaming into the void before disappearing forever, beyond the event horizon. The implications of something being able to exert gravitational influence without allowing anything to escape raise fundamental questions. These questions strike at the heart of causality, information, and the very nature of physical forces. If we accept that nothing can travel faster than light and simultaneously observe that light cannot escape a black hole, a crisis of physics emerges. The very existence of external gravitational effects seems to violate the most basic principles we hold dear. This paradox threatens our coherent understanding of the cosmos, threatening to unravel the tapestry of modern science. For generations, scientists and philosophers have wrestled with this apparent contradiction in the dark. If gravity needed to travel from the inside of the black hole to the outside to exert its influence, it would face an insurmountable barrier. It should be subject to the exact same limitations that prevent light from escaping. But clearly, looking at the celestial mechanics around us, this is not what we observe. Black holes exert undeniable gravitational attraction, maintain perfectly stable orbits, and actively participate in the cosmic dance of galaxies. The paradox becomes even more baffling when we consider the practical implications for modern astronomy. Astronomers can detect these dark behemoths precisely through their gravitational effects on nearby objects. We observe stars orbiting invisible companions, accelerating to speeds that can only be explained by the presence of extremely massive and compact objects. If gravity could not escape these objects, they would be completely undetectable and irrelevant to the rest of the universe. They would be ghosts, having no physical tether to the galaxies they inhabit. But this is where our perspective begins to fundamentally change, revealing that the paradox itself is an illusion. It is based on an incomplete and somewhat archaic understanding of what gravity really is. For centuries, we have thought of gravity as a force that acts at a distance, a rigid tether between masses. We imagined it as something that massive objects actively send through space to influence other objects. This Newtonian perspective, while extraordinarily useful for building bridges and launching rockets, has severe limits. It has led us to ask questions that contain incorrect assumptions about the fundamental nature of gravitation. The core question, how does gravity escape? It presupposes that gravity is an entity that needs to escape from somewhere. It assumes that gravity is a signal that originates inside the black hole and must travel outward to exert its influence. This assumption is deeply rooted in our everyday terrestrial intuition about forces and effects, and it is precisely this flawed human intuition that creates the apparent paradox. Let's consider a simple analogy that begins to illuminate the resolution to this cosmic riddle. The event horizon represents one of the most elegant yet deeply disturbing concepts in modern physics. It is not a material barrier like the rocky surface of a planet or the burning atmosphere of a star. It is instead a literal point of no return defined by the pure, unyielding geometry of curved spacetime. Once anything, whether a photon of light, a stray atom, or a doomed spaceship, crosses this invisible border, its fate is sealed. The mathematical definition of the event horizon is deceptively simple, yet it holds profound significance for the universe. It is the exact place where the escape velocity equals the absolute speed limit of the universe, the speed of light. This alignment of 299,792,458 meters per second is not a mere numerical coincidence. It reveals a fundamental, deep-seated connection between the universe's speed limit and extreme space-time geometry. To truly understand what this definition means in practice, we must look at the concept of escape velocity. From the surface of the Earth, a rocket needs to reach approximately 11 kilometers per second to permanently escape gravity. This speed, although monumental by human engineering standards, represents a minuscule fraction of the speed of light. The Moon, with its much weaker gravitational grip, requires an escape velocity of just 2.4 kilometers per second. The Sun, massive but widely distributed, requires escape velocities of 618 kilometers per second from its burning surface. Even this incredible solar speed is still only a fraction of 2% of the speed of light. But when a sufficient amount of mass is aggressively concentrated into a sufficiently small volume, physics breaks down. The escape velocity progressively approaches the speed of light until, at a critical threshold, the two are exactly equal. This critical threshold defines the event horizon, creating a sphere of perfect, inescapable darkness. The scale of compression required to achieve this state completely defies human imagination. If the entire mass of the Earth were compressed until its radius was only 0.8 times 10 to the power of 0.8 cubic centimeters, it would become a black hole. The event horizon would sit exactly on this spherical surface, the size of a large marble, locking the interior away forever. For the outside universe, our Sun would require violent compression down to a radius of approximately 3 kilometers. Sagittarius A, the supermassive monster at the center of our galaxy, has an event horizon of 12 million kilometers. It is smaller than the orbit of Mercury, yet contains the crushed mass of over 4 million suns. What makes the event horizon truly extraordinary is not its physical size, but its nature as an absolute causal boundary. Inside the event horizon, space and time twist so severely that all possible future paths lead inward. There is no physical trajectory, no matter how powerful your engines, that points back to the outside universe. This impossibility is not a mere technological limitation waiting for better spaceship engineering. It is a fundamental, hard-coded prohibition built directly into the fabric of space-time itself. The interior of the black hole becomes causally disconnected from the exterior in an absolute, terrifying way. The invisible nature of the event horizon creates one of the strangest experiential situations in all of physics. An astronaut falling toward a supermassive black hole would experience nothing special upon crossing the horizon. There would be no flashing warning signs, no physical bump, no sensation of crossing a tangible barrier. They would pass the absolute point of no return without a single local alarm going off. Long pause. Space-time would seem locally normal to them, behaving according to the standard physical laws of free fall. This local normality is the ultimate illustration of Einstein's equivalence principle in action. There is no local, enclosed experiment an observer can perform to detect the presence of the event horizon. Inside the horizon, the doomed traveler would continue to fall, unaware of their permanent isolation. However, from the perspective of external observers watching from afar, the visual story is radically different. For someone observing from a safe distance, time near the event horizon slows down dramatically. This effect, known as gravitational time dilation, makes approaching clocks appear to tick agonizingly slow. As an object approaches the mathematical limit of the horizon, its time seems to stop completely to the outside world. This bizarre difference in temporal experiences creates one of the most fascinating apparent paradoxes of observation. From the external perspective, nothing ever truly appears to cross the event horizon. Observers would see the falling object progressively slow down, its image becoming increasingly dim and red. The light loses energy fighting the gravity, effectively fading from view, while remaining technically frozen on the edge forever. Yet, for the falling object itself, the crossing of the event horizon occurs in finite, unremarkable normal time. The traveler experiences no subjective temporal slowdown, no freezing of their own reality. As they fall, they would experience the terrifying phenomenon known as spaghettification, where tidal forces stretch their body. The traveler continues their dark plunge toward the central singularity, experiencing time normally until the very end. This duality of temporal perspectives reveals something profound about the relative, flexible nature of time itself. There is no single, correct, absolute time frame to describe events in the universe, especially near extreme gravity. Both perspectives, the frozen external view and the fatal internal view, are physically valid in their own frames. The event horizon also serves as an absolute, impenetrable informational boundary. No information about events occurring inside the horizon, no light, no radio signal, can ever reach the outside. This creates a region of space-time permanently cut off from communicating with the rest of the cosmos. This informational incommunicaglie severely challenges our traditional understanding of causality and determinism. Events inside the horizon cannot causally influence anything outside, creating a state of absolute isolation. However, we must fiercely remember that this incommunicaglie does not apply to the black hole's own gravitational field. The curvature of space-time characterizing the black hole's mass is not information trying to exit from the inside. This curvature was established long ago, during the original gravitational collapse that birthed the black hole. It remains safely encoded in the geometry of the exterior spacetime, completely unaffected by the horizon's censorship. This vital distinction is the definitive key to resolving the paradox of how gravity escapes. Specific events occurring inside the event horizon are effectively censored and deleted from the outside universe's ledger. But the very existence of the black hole, its mass, its spin, and its charge remain prominently advertised on the outside. It is aimed to view the curvature of the exterior space-time, perfectly accessible to any distant observer with a telescope. The event horizon represents the most dramatic, unforgiving boundary in the entire known universe. It defines a stark division between regions of space-time that operate under fundamentally different rules of communication. It is an invisible border that changes the destiny of anything that crosses it with absolute finality. Understanding the event horizon as an absolute causal limit, rather than a physical shell, is crucial. It explains why the gravity of black holes does not face the limitations of a trapped signal. Gravity does not need to cross the event horizon because it was already present in the exterior curvature. It was established before the event horizon even existed, maintained by the continuous geometry of space-time. The event horizon thus reveals its true, passive nature. It is not an active prison keeping gravity contained, but a mathematical boundary defining extreme geometry. Gravity itself transcends this boundary because gravity is the very geometric structure that creates the boundary. To truly grasp how gravity transcends these apparent limitations, we must reshape our mental models of space. We must visualize space-time as a dynamic, flexible fabric, capable of bending under extreme stress. It creates a geometry that is as physically real and tangible as the mountains and valleys on Earth. This geometric visualization is not just a helpful metaphor, it is the literal mathematical truth of general relativity. Massive objects modify the geometric structure of space-time, creating depressions that naturally dictate movement. Imagine the two-dimensional elastic membrane, the perfectly taut trampoline we discussed earlier. Placing a bowling ball in the center creates a real, physical depression that alters the shortest paths across the surface. Marbles rolling across this trampoline don't need a magnetic force to circle the heavy ball. They simply follow the straightest possible lines across a surface that has been severely curved. The planets in our solar system operate on this exact same principle, just in 4 dimensions. They are following geodesics, the most direct paths available through the space-time curved by the massive Sun. The Earth orbits the Sun merely because it is following the natural geometry of curved space. This curvature extends outward in all directions, fading in intensity but never truly dropping to zero. This curvature is not an emission, it is a direct, static modification of the cosmos's geometric structure. Now, let's carefully trace how this curvature is established during the violent birth of a black hole. During the collapse of a massive dying star, stellar matter is violently compressed inward by its own weight. This process creates increasingly intense, localized space-time curvatures that ripple outward. When the collapse reaches the critical point of forming an event horizon, the interior geometry becomes extreme. All geodesics inside suddenly point inward toward the singularity, creating the ultimate trap. But critically, the curvature outside the event horizon remains largely unaltered and stable. It maintains the exact same gravitational intensity it had when the original star was still shining bright. This persistence of the exterior curvature is the definitive answer to our original paradox. The gravitational pull we feel from a black hole did not magically escape from the inside after formation. It is the legacy curvature established during the original gravitational collapse, permanently encoded outside. Returning to the trampoline analogy, imagine increasing the weight of the ball until the fabric stretches infinitely downward. The central pit becomes bottomless, but the outer edges of the depression maintain their established slope. This geometric continuity explains a fascinating fact. A black hole's gravity feels normal from afar. If the Sun were magically and instantly replaced by a black hole of the exact same mass, our orbit would not change. The Earth would continue orbiting in the dark, exactly as before, completely unaware of the change. The curvature of space-time at Earth's distance depends only on total mass, not its compression. This explains why information about the mass of a black hole remains perfectly accessible to us. It is encoded directly in the shape and intensity of the exterior space-time curvature. This geometric encoding is analogous to how a mountain's shape tells us about the tectonic forces that formed it. You don't need to dig into the Earth's mantle to infer information about the forces that pushed the rock upward. Similarly, you don't need to pierce the event horizon to weigh a black hole. The geometric nature of gravity also perfectly predicts the existence and behavior of gravitational waves. These waves are dynamic ripples in the curvature of space-time caused by the violent acceleration of huge masses. When 2 black holes spiral toward each other, their chaotic movements whip space-time into a frenzy. They create ripples that propagate outward, carrying massive amounts of energy away from the binary system. It's clearly exactly what contributes to the event horizon as a contract to hell. This energy loss is radiated by the system as a whole through the geometric fabric, not from inside the holes. The detection of these waves by LIGO has provided direct, stunning confirmation of Einstein's century-old math. It confirms that gravity behaves as ripples in curvature, traveling strictly at the speed of light. The curved geometry of space-time also provides mind-bending insights into the fluid nature of time. Intense gravity doesn't just bend space, it drags and slows the flow of time itself. Clocks objectively run slower in regions of intense curvature, a confirmed phenomenon known as time dilation. Near the edge of a black hole, this dilation becomes so extreme that time practically grinds to a halt for outsiders. Understanding gravity as geometry also reveals why it is perfectly universal in its effects on all matter. All objects, regardless of mass or composition, respond identically to the curves of spacetime. A feather and a hammer fall at the same rate in a vacuum because they are following the same geometric path. Gravity does not discriminate. It affects everything that exists within the fabric of space. This universality contrasts sharply with electromagnetic forces, which only affect charged particles. The elegance of this geometric description unifies falling apples, orbiting planets, and bending light. It unifies the slowing of clocks and the rippling of gravitational waves under one coherent framework. And most importantly, it provides the final, unassailable resolution to our original paradox. Gravity does not escape from black holes because it was never inside them in any conventional sense. Gravity is the curvature extending from the horizon outward, influencing the cosmos at vast distances. It is as permanent and stable as a valley carved into a mountain range. It does not need to be maintained by a continuous stream of escaping messenger particles. It is an intrinsic feature of spacetime that persists simply because the geometry itself persists. Near a black hole, we encounter phenomena that profoundly challenge our biological notions of time's universality. Two observers, one safe and distant, one falling inward, can witness the exact same physical events differently. They experience temporal sequences so radically divergent they seem to inhabit completely separate realities. This temporal divergence is not an optical illusion or a flaw in their clocks. It is fundamental physics. It is a harsh manifestation of how extreme gravity actively transforms the flow of time. This duality reveals one of the most difficult truths of general relativity for humans to accept. There is absolutely no universal cosmic clock ticking at the same rate for everyone. Each observer carries their own personal time, their own reality, dictated by their local gravity and speed. This shatters our most fundamental conceptions about the shared objectivity of physical reality. Concepts like simultaneous, before, and after lose their absolute meaning across different gravitational zones. Long pause. To fully grasp this, imagine two twin astronomers, Anna and Carlos, investigating a black hole. Anna remains stationary, far away, while Carlos ventures dangerously close to the event horizon in his ship. They start with perfectly synchronized atomic clocks and continuous radio communication. Initially, far from the black hole, their experience of time is virtually identical and communications are normal. However, as Carlos descends into the gravity well, a fascinating and terrifying divergence begins. From Anna's distant perspective, Carlos's clock begins to tick noticeably and progressively slower. As he reaches 10 Schwarzschild radii, his clock runs 5% slower, and his radio voice drops in pitch. The light from his ship loses energy fighting the gravity, stretching into longer, redder wavelengths. At 5 radii, the discrepancy grows. Carlos's time runs 15% slower to Anna's eyes. His communications arrive with agonizing delays, his words drawn out in a deep, distorted slow motion. As he nears the mathematical limit of the horizon, Anna watches his time slow down asymptotically until it stops. From her external view, Carlos never actually crosses the threshold. He freezes eternally on the edge. His image slowly fades to black as the redshift becomes infinite, but technically he remains there forever. This creates a haunting paradox. To the outside universe, things fall in, but never quite seem to finish falling. But Carlos's own subjective experience of this doomed journey is radically, violently different. Inside his ship, his clock ticks normally, his heart beats at a regular pace. He experiences absolutely no temporal slowdown, no freezing, no sluggishness in his own reality. Looking back at Anna, he sees her signals arriving faster, blue shifted, her universe seemingly hitting fast forward. When Carlos finally reaches the event horizon, he crosses it in a finite, perfectly normal moment of his time. There is no dramatic freezing. He crosses the ultimate point of no return as an ordinary local event. This confirms Einstein's equivalence principle. Local physics remains normal even in extreme curvature. After crossing, Carlos continues to experience normal time as he plummets toward the inescapable singularity. However, his ability to send any message back to Anna has been permanently severed by the geometry of space. This duality proves that there is no single correct temporal perspective in the universe. Both Anna's frozen view and Carlos's fatal plunge are physically valid within their own specific frames. This extreme temporal relativity also has fascinating, complex implications for the conservation of quantum information. From Anna's perspective, the information making up Carlos never truly enters the black hole. It remains eternally smeared and suspended at the event horizon, preserved in the exterior spacetime curvature. This realization helps resolve the infamous black hole information paradox that haunted Stephen Hawking. It suggests that information is not destroyed, but encoded holographically on the boundary, accessible in principle. The temporal divergence explains perfectly why the gravity of the black hole remains accessible to the outside. The gravitational curvature was established during the original collapse, in the spacetime where time still flows for Anna. Time is a dynamic dimension that responds locally to mass, allowing gravity to transcend apparent limits. Gravity doesn't need to escape because it resides in the regions of spacetime that were never disconnected. This brings us to one of the most extraordinary, mind-bending revelations about black holes and information. In a very real, measurable sense, information never completely disappears into the dark void. From our external viewpoint, all information about falling objects is permanently painted onto the horizon's surface. It creates a complete, scrambled cosmic library of everything that ever dared to approach the abyss. This preservation is not abstract philosophy. It impacts our core understanding of physical reality. The extreme time dilation freezes the infalling information at the horizon, preventing its total erasure. Every atom of a doomed spaceship remains encoded in the space-time structure near the boundary. The information is redistributed and scrambled in ways that defy our ordinary concepts of data storage. Black holes function as the most secure, perfect cosmic archives in the entire universe. Every photon, every particle leaves a permanent, microscopic imprint on the exterior space-time geometry. This resolves the fear that black holes violate quantum mechanics by permanently destroying data. The information remains accessible, albeit highly encrypted, preserving the mathematical consistency of physics. This holographic encoding is precisely why we can measure a black hole's mass, spin, and charge from afar. These properties are not trapped, they are prominently displayed on the horizon's surface for the universe to see. When we observe the orbits around Sagittarius A Power, we are reading this holographic information directly. The holographic principle suggests that all 3D information inside can be encoded on the 2D surface boundary. Black holes provide the most extreme, literal example of this holographic reality in action. It implies the 3D interior of a black hole might actually be mathematically redundant. All necessary data to describe the system is present on the surface, accessible to external observers. This redundancy guarantees that the black hole's gravity remains fully specified by external, observable data. When two black holes merge, a process we routinely detect, their surface information must be reorganized. The chaotic merger scrambles and redistributes the holographic data onto the new, larger event horizon. This dynamic reorganization maintains total information conservation throughout the violent collision. Gravitational waves carry the precise details of this merger, radiating the changing information outward. This suggests that the strict distinction between the interior and exterior of a black hole might be an illusion. The gravitational information was never causally disconnected. It was always encoded on the outside. Black holes might be the most permanent structures in the universe, outliving stars and galaxies. While stars burn out and galaxies drift apart, the information on an event horizon remains deeply stable. It is protected by the very resilient structure of spacetime itself, lasting for unimaginable cosmological epochs. Future research continues to unravel the profound implications of this holographic preservation of data. It could reveal revolutionary new principles linking geometry, gravity, and quantum information theory. The understanding that information freezes in time, remaining accessible, is the final piece of the paradox puzzle. Gravity doesn't need to escape because the data specifying that gravity was never truly locked away. It always remained intimately connected to the exterior universe, painted on the edge of the abyss. This transforms black holes from absolute prisons of destruction into sophisticated, eternal cosmic archives. The gravitational ecology of the universe, capable of forming binary pairs, interacting over long periods, and eventually merging in events that reshape the local geometry of spacetime. Future generations of gravitational wave detectors promise to reveal even more extraordinary details about the dance of binary black holes. More sensitive detectors will be able to observe the in-spiral phases for much longer periods, potentially tracking binary systems for days or weeks before their final mergers. This extended observational capability will allow unprecedented precision measurements of black hole parameters, including tests of the most subtle predictions of general relativity in strong field regimes. It will also allow detailed studies of how black holes exchange energy and angular momentum during their prolonged binary interactions. The dance of binary black holes thus definitively reveals that gravity is not imprisoned within event horizons. These extreme objects can communicate, interact, and influence each other in ways that are only possible if their gravitational fields are fully accessible externally. The elegance of this cosmic dance lies in how it demonstrates that black holes, far from being isolated gravitational prisons, are dynamic participants in the gravitational ballet of the cosmos, capable of complex interactions that culminate in some of the most energetic events. As our journey tonight comes to an end, we have discovered that the great paradox that terrified physicists was not an error of the universe, but a flaw in our way of looking at it. Gravity doesn't need to escape from black holes for a simple and beautiful reason. It was never trapped in the first place. It is the indelible imprint on the fabric of space-time, the eternal and geometric scar left by a collapsing star. Long pause. We have learned that the event horizon is not the ultimate abyss where everything is lost, but a perfect cosmic archive, a place where information freezes holographically at the edge of time. A long pause, and thanks to the echoes captured by LIGO, today we know that these invisible titans are not lonely monsters, but dynamic dancers that collide and merge, making the very fabric of reality vibrate. It is profoundly poetic, isn't it? That the darkest, strangest, and seemingly most destructive objects in creation are, in reality, the ones that shed the most light on the fundamental laws of our cosmos. The next time you step outside and look up at the night sky, remember that the dark space between the stars is not an empty stage. It is alive. It bends, it stretches, it breathes, and it vibrates with the unbreakable gravity of stellar ghosts. Thank you for joining me on this journey beyond light, time, and everyday logic. If this exploration has challenged your mind and expanded your universe, I invite you to subscribe and leave your thoughts in the comments. Never stop questioning the obvious. Never stop wondering at the invisible. This was Nocturnal Science. This was Nocturnal Science. Until the next adventure, and have a deep, serene, and inspiring night. On September 14th, 2015, at 9:50 and 45 seconds UTC, a monumental event occurred on Earth. In two locations separated by 3,000 kilometers, an extraordinary signal finally reached our planet. Two of the most sensitive instruments ever built detected a whisper that had traveled for 1.3 billion years. This signal was not light, not radio, nor any conventional radiation humanity had ever seen. It was a direct, physical ripple in the fabric of space-time itself, a gravitational wave. It carried the energetic signature of two massive black holes merging in a final, violent cosmic dance. The successful detection by LIGO represented the ultimate triumph of Einstein's general relativity. It provided irrefutable proof that gravity behaves as dynamic ripples, propagating at the exact speed of light. This confirms that gravitational waves face the same fundamental speed limits as everything else in the cosmos. If gravity were a trapped force, these waves could never have escaped the merging black holes. But LIGO proved that these waves are not signals sent from inside. They are ripples made of the space outside. They propagate outward from the violently shaking exterior geometry, carrying immense energy. To appreciate LIGO, we must understand the sheer, terrifying precision of these giant interferometers. They consist of 4-kilometer-long vacuum tubes arranged in an L shape, firing pristine lasers at perfect mirrors. The mirrors inside LIGO are some of the smoothest, most perfectly polished objects ever created by human hands. When a gravitational wave passes, it physically stretches and compresses the space inside these tubes. LIGO can detect a change in distance smaller than a 10,000th of a trillionth of a proton's diameter. It is like measuring the distance to the nearest star and noticing it changed by the width of a hair. This first detection, GW150914, revealed two black holes of 29 and 36 solar masses merging into one. They had spiraled together for millions of years, actively communicating their gravity to each other. If their gravity was trapped, they could not have maintained their orbit or pulled each other into a collision. Their orderly, predictable merger proves their gravitational fields interacted freely in the exterior space. The energy they lost during their spiral was radiated outward as waves in the space-time fabric. This radiation proves that the movement of mass actively churns the geometry of the surrounding universe. The detected waves allowed scientists to determine the masses, spins, and distances of these invisible ghosts. All this intricate data was perfectly encoded in the specific shape and frequency of the space-time ripples. This accessibility proves the information defining a black hole's gravity lives on the outside, available to us. Since 2015, LIGO and Virgo have detected dozens of these catastrophic mergers across the deep universe. They have also detected neutron star mergers, which produce both gravitational waves and visible light bursts. The simultaneous arrival of both signals proved conclusively that gravity travels exactly at the speed of light. Both forces are subject to the same fundamental speed limit, governing causality in our universe. These detections have opened a revolutionary new window for humanity to hear the dark universe. They revealed that black holes are far more common, massive, and diverse than our early models predicted. The existence of these ancient binary systems proves black hole gravity is remarkably stable over cosmic time. It doesn't fade or weaken. It is a permanent feature of the curved space-time fabric. The precise shapes of the waveforms allow us to test general relativity in the most extreme gravity environments. So far, Einstein's century-old math has held up flawlessly against the most violent events in nature. Future detectors will look deeper, potentially observing mergers from the very dawn of the universe. Space-based detectors like LISA will listen to the low-frequency hum of supermassive black holes colliding. This new astronomy might even detect the faint gravitational echoes of the Big Bang itself. LIGO has transformed black holes from theoretical curiosities into active, loud participants in the cosmic ecosystem. They are not isolated sinks that devour everything without a trace. They shape and shake the universe around them. The evidence from LIGO definitively ends the debate. Gravity is not trapped inside the event horizon. Gravitational waves emerge from the highly agitated space-time exterior, freely traveling across the cosmos. To understand the origin of this exterior gravity, we must look back to the terrifying birth of the black hole. The catastrophic collapse of a massive star is an event whose consequences endure for eons. The curvature we observe today was established during the frenzied moments of this initial collapse. It is a metamorphosis that takes a burning star and crushes it into an extreme geometric anomaly. During this violent process, the defining curvature is permanently engraved into the surrounding spatial fabric. Imagine a supergiant star, 30 times heavier than our Sun, burning brightly in a distant galaxy. For millions of years, it maintains a delicate balance between outward nuclear pressure and inward gravity. This balance allows it to shine, fighting off the crushing weight of its own massive outer layers. But massive stars live fast, furious lives, rapidly burning through their limited nuclear fuel. They fuse hydrogen, then helium, carbon, neon, oxygen, and silicon in a desperate bid to stay alive. Finally, they fuse silicon into iron, and the star faces a sudden, terminal energy crisis. Fusing iron requires energy rather than releasing it, instantly removing the core's outward pressure support. In less than a second, an iron core the size of Earth collapses into a sphere just 20 kilometers wide. The sheer violence required to crush a star into a single point is beyond human comprehension. This sudden, catastrophic compression violently warps the geometry of the surrounding space-time. The increasing density creates an incredibly intense, localized curvature that ripples outward. Crucially, this extreme space-time curvature is established while the star is still actively collapsing. It is established before the dark veil of the event horizon has fully formed to trap the light. During these initial stages, the star is still visible and causal communication with the outside is still possible. The gravitational curvature is imprinted on the exterior space during this exact critical window. It modifies the local cosmos in ways that will persist long after the star's matter crosses the point of no return. As the collapse completes, the curvature reaches a critical threshold, defining the event horizon. The surface becomes a mathematical demarcation in curved space where light speed is no longer enough. When the matter falls past this line, it is gone from the visible universe forever, cloaked in darkness. But the exterior space-time curvature, already established, remains perfectly unaltered and unaffected. It becomes a permanent, frozen imprint of the collapse process, preserved in the geometry of the void. The newly formed black hole does not need to actively maintain this curvature with continuous signals. It persists simply because the modified geometric properties of space-time have been permanently set. Think back to the trampoline. The deep slope is established as the heavy ball sinks into the fabric. Once the steep slope is formed, it remains stable, dictating the paths of marbles far away from the center. This explains why replacing the Sun with a solar mass black hole wouldn't change Earth's orbit. The exterior curvature depends purely on total mass, remaining identical regardless of the central density. The formation of the event horizon is an internal feature that does not rewrite the external gravitational field. This geometric stability ensures that black holes can persist for periods of time that defy comprehension. They will likely outlive the stars, persisting in the cold, dark future of the universe long after galaxies fade. The exterior curvature allows black holes to naturally interact, guiding them into binary orbits. As they orbit, their respective space-time curvatures overlap, creating highly complex, dynamic geometric patterns. This interaction relies entirely on the superposition of exterior curvatures, requiring no information from the inside. The radiation of gravitational waves emerges from the violent churning of this combined exterior geometry. As they lose energy to these waves, their orbit tightens, inevitably leading to a spectacular, destructive merger. During the merger, the individual curvatures violently snap together to form a new, unified geometric shape. This releases the most intense burst of gravitational wave energy detectable in our current cosmos. The legacy of the original stellar collapse is preserved, passed on, and modified through generations of mergers. The supermassive black holes in galactic centers carry the geometric memory of countless ancient collisions. The curvature we observe today was established during the chaotic dawn of galactic formation. This understanding, that curvature is established during collapse and remains external, is the final resolution. Gravity was never waiting inside a dark prison, struggling to break free from the event horizon. The curvature we perceive was imprinted on the exterior long before the prison doors even closed. It is as real, tangible, and permanent as the mountains carved into a terrestrial landscape. It persists indefinitely as an inherent feature of geometry, influencing the cosmos with its silent pull. The solution to the paradox is elegant and simple. There is no escape necessary because there was never imprisonment. 1.3 billion light-years away, two black holes executed a cosmic dance of epic proportions for millions of years. Each the mass of 30 suns, compressed into spheres just a few hundred kilometers wide, spiraling together. They were inexorably drawn toward a merger that would briefly outshine all the stars in the observable universe in wave energy. This binary dance is not just energetic, it reveals the fundamental nature of gravity near these dark extremes. Throughout their courtship, these black holes communicated gravitationally in ways impossible if gravity were trapped. The evidence of this continuous, fluid gravitational communication is irrefutable, recorded by our detectors. They maintained stable orbits, continuously adjusting trajectories in response to the shifting mass distribution. They exchanged angular momentum, locking into a synchronized orbital rhythm to conserve the system's total spin. Over millions of years, they slowly bled energy into the cosmos through the continuous emission of gravitational waves. This slow, predictable loss of energy caused their orbits to shrink with agonizing precision over eons. But as they drew closer, the dynamics of their interaction accelerated into a chaotic, violent frenzy. The intensity of their gravitational communication amplified. Mutual tidal forces tore at the surrounding space. The loss of energy accelerated exponentially, and the orbital contraction became a rapid death spiral. In their final days, they orbited each other every few hours. In their final seconds, dozens of times a second. This extreme acceleration demonstrates they responded instantly to changes in their companion's gravity. Causal delays from trapped gravity would have made this rapid, stable in-spiral physically impossible. The extreme precision with which we can predict these specific waveforms provides ultimate validation. We can model them perfectly by treating black holes as objects defined entirely by external parameters: mass, spin, charge. We require zero knowledge of the internal processes inside the horizons to calculate the waves LIGO detects. This proves all necessary information to describe their interactions is freely accessible on the outside. The binary dance shows how the space-time curvature of two black holes overlaps, creating complex, amplified regions. As they close the distance, the interaction between their curvatures becomes highly non-linear and incredibly complex. They move through regions where curvature changes rapidly in intensity, generating the cosmos's most intense waves. This highly complex interaction occurs completely in the exterior space-time, never needing to cross the horizons. The final merger is one of the most violent, transformative, and perfectly executed events in the universe. In the final milliseconds, orbiting at fractions of the speed of light, extreme relativistic effects take hold. Length contraction, severe time dilation, and massive frame dragging severely warp the local geometry. The individual curvatures reorganize violently, snapping together to form a new, single, unified shape. This geometric reorganization converts several solar masses directly into pure gravitational wave energy. The resulting merged black hole is perfectly predictable from the initial conditions of the two progenitors. It has slightly less mass than the sum of its parts, the difference radiated away during the violent union. This Measuring this exact mass loss provides direct, stunning experimental verification of Einstein's E equals mc squared. It confirms this fundamental relationship in the most extreme, high-energy regime ever observed by humanity. Observations reveal these black holes can have extremely high spins, rotating at terrifying fractions of light speed. This rapid rotation creates frame dragging, where the black hole literally pulls the surrounding space along with it like a whirlpool. This modifies the orbital dynamics, leaving distinct, recognizable signatures in the gravitational wave signals we detect. These spin measurements offer vital clues about how these specific black holes formed and evolved over time. The high population of binary systems detected suggests these cosmic collisions are a common, natural occurrence. Black holes are not isolated phenomena. They are highly active, interactive participants in the universe's ecology. Future, more sensitive detectors will observe these in spiral phases for weeks or months before the final merger. This will allow unprecedented precision tests of general relativity in the strongest gravity fields imaginable. The dance of binary black holes definitively, beautifully reveals that gravity is not imprisoned in the dark. These extreme objects communicate and influence each other freely because their gravitational fields are completely external. The elegance of this cosmic dance proves that black holes are dynamic participants in the universe's grand ballet. They are the architects of some of the most energetic, profound, and illuminating events in the observable cosmos. From the depths of the mathematical paradox, we have emerged with a clearer, more breathtaking view of reality. Gravity is the invisible landscape of the universe, shaping the paths of light and matter alike. It is the language through which the cosmos communicates its structure, unhindered by the darkness of the event horizon. The next time you look up at the night sky, remember that the dark voids are not empty. They are filled with the silent, rippling echoes of colliding titans, telling the story of a universe far stranger than we ever imagined. The final merger of the black holes represents one of the most violent and transformational events in the universe. During the last milliseconds, before their event horizons touch and merge, the black holes can be orbiting each other at speeds reaching significant fractions of the speed of light. These extreme speeds create dramatic relativistic effects that warp the visual universe around them. The black holes experience severe length contraction, flattening into disks from the perspective of a stationary observer. They also experience extreme time dilation, where their local clocks practically freeze compared to the rest of the cosmos. Massive frame-dragging effects occur, modifying the local geometry of spacetime in ways only possible in these extreme velocity regimes. The space around them is whipped into a frenzy, twisting like a tornado made of pure vacuum. During the merger proper, the individual curvatures of the black holes reorganize violently to form a new unified curvature. The two event horizons stretch out toward each other, forming a bridge of darkness before snapping into a single, highly distorted sphere. This distorted new horizon wobbles furiously, vibrating like a struck bell in a process known as the ring down. This process of geometric reorganization releases enormous amounts of energy in the form of gravitational waves. It is typically equivalent to the conversion of several solar masses directly into pure energy in less than a second. For a brief instant, this single collision generates more power than all the light emitted by all the stars in the observable universe. The new unified curvature that emerges from the merger perfectly encodes the properties of the resulting black hole. Its total mass, its angular momentum, and its electric charge are the only features that survive the union. These properties are determined by strict conservation laws applied to the progenitor black holes. The final result is completely predictable from the initial conditions of the binary system, a triumph of deterministic physics. The resulting merged black hole typically has a mass slightly less than the sum of the masses of its progenitors. The missing mass hasn't vanished. The difference has been radiated away as gravitational wave energy during the merger process. This missing mass is directly measurable through the careful analysis of the detected gravitational waveforms on Earth. The ability to precisely measure this mass loss provides direct, undeniable experimental verification of Einstein's most famous equation. E equals mc squared. The equivalence of mass and energy plays out on the grandest stage imaginable. The energy radiated in gravitational waves corresponds exactly to the lost mass multiplied by the speed of light squared. This confirms this fundamental relationship in the most extreme, chaotic energy regime ever observed by humanity. Observations of binary mergers have also revealed that black holes can have extremely high angular momenta, or spins. Some are found to be rotating at significant fractions of the maximum theoretical rotation speed allowed by general relativity. This rapid rotation creates intense frame-dragging effects, where the black hole literally drags the surrounding space-time into its rotation. Spoon is stirring thick honey. The black hole stirs the very fabric of the cosmos around it. Frame dragging is particularly important in binary systems because it profoundly modifies the orbital dynamics. It alters the path of the black holes in ways that are perfectly detectable in the gravitational waveforms we capture. Rapidly rotating black holes create orbital precession effects, causing their orbital plane to tilt and wobble. These wobbles leave characteristic, unmistakable signatures in the gravitational wave signals, acting like a cosmic fingerprint. These signatures allow scientists to measure not only the magnitudes of the spins, but also their relative orientations to each other. These precise spin measurements provide immensely valuable information about the hidden processes of black hole formation. High aligned spins suggest histories of prolonged accretion or formations from the same swirling gas cloud. Conversely, low or misaligned spins may indicate formation through violent, chaotic interactions in dense star clusters. The sheer population of binary black holes detected by LIGO has revolutionized our statistical understanding of the universe. It has revealed that these dark binary systems are much more common than astronomers had previously anticipated. Detection rates suggest that black hole mergers occur somewhere in the local universe approximately once every few minutes. This implies a total hidden population of binary systems that far exceeds the predictions of many traditional stellar synthesis models. This abundance of binary systems demonstrates that gravitational interactions between black holes are natural, ubiquitous phenomena in the cosmos. Black holes are not isolated, rare objects that silently absorb everything without interacting. They are active, essential participants in the vast gravitational ecology of the universe. They are capable of forming binary pairs, interacting over cosmological periods, and eventually merging in spectacular fashion. These events completely reshape the local geometry of space-time, sending ripples through the dark ocean of the void. Future generations of gravitational wave detectors promise to reveal even more extraordinary details about this dance. More sensitive detectors will soon be able to observe the subtle in-spiral phases for much longer periods. They will potentially be capable of tracking binary systems for days, weeks, or even years before their final, fatal mergers. This extended observational capability will allow for unprecedented precision measurements of black hole parameters. It will enable tests of the most subtle, complex predictions of general relativity in strong field regimes. It will also allow detailed studies of exactly how black holes exchange energy and angular momentum during their prolonged binary interactions. The dance of binary black holes thus definitively and beautifully reveals that gravity is not imprisoned within event horizons. These extreme objects can communicate, interact, and influence each other in ways that rely entirely on exterior geometry. This continuous interaction is only possible if their gravitational fields are fully, permanently accessible externally. The elegance of this cosmic dance lies in how it shatters the illusion of the black hole as a dark prison. It demonstrates that black holes, far from being isolated traps, are dynamic participants in the gravitational ballet of the cosmos. They are capable of complex interactions that culminate in some of the most energetic and illuminating events ever witnessed. From the depths of a theoretical paradox, we have emerged with a profound, breathtaking view of reality. Gravity is the invisible, undulating landscape of the universe, shaping the paths of light and matter alike. It is the fundamental language through which the cosmos communicates its structure, entirely unhindered by the darkness of the event horizon. The next time you look up at the night sky, remember that the dark voids are not empty spaces. They are filled with the silent, rippling echoes of colliding titans. These echoes tell the story of a universe far stranger and far more connected than we ever imagined. As our journey tonight comes to an end, we have discovered that the great paradox that terrified physicists was not an error of the universe, but a flaw in our way of looking at it. Gravity doesn't need to escape from black holes for a simple and beautiful reason. It was never trapped in the first place. It is the indelible imprint on the fabric of space-time, the eternal and geometric scar left by a collapsing star. We have learned that the event horizon is not the ultimate abyss where everything is lost. Instead, it acts as a perfect cosmic archive, a boundary where information freezes holographically at the edge of time. And thanks to the echoes captured by LIGO, today we know that these invisible titans are not lonely monsters. They are dynamic dancers that collide and merge, making the very fabric of reality vibrate with their power. It is profoundly poetic, isn't it? That the darkest, strangest, and seemingly most destructive objects in creation are, in reality, the ultimate teachers. They are the ones that shed the most light on the fundamental, unbreakable laws of our cosmos. The next time you step outside and look up at the night sky, remember that the dark space between the stars is not an empty stage. It is alive. It bends, it stretches, it breathes, and it vibrates with the unbreakable gravity of stellar ghosts. Thank you for joining me on this journey beyond light, time, and everyday logic. If this exploration has challenged your mind and expanded your universe, I invite you to subscribe and leave your thoughts in the comments. Never stop questioning the obvious. Never stop wondering at the invisible forces that shape our reality. This was Nocturnal Science. Until the next adventure, have a deep, serene, and inspiring night. But wait, before we completely fade into the dark, there is one final secret to uncover. What happens when eternity finally runs out of time? For decades, we believed that black holes were immortal, permanent fixtures of the cosmos. For decades, we thought that once a black hole formed, it would sit in the void forever, growing larger as it consumed matter. It seemed they were the final, indestructible tombstones of the universe. But in the 1970s, a brilliant physicist named Stephen Hawking turned this absolute certainty upside down. He decided to look at the event horizon not just through the lens of Einstein's gravity, but through the microscopic rules of quantum mechanics. What he found shocked the scientific community and forever changed our understanding of the void. Hawking realized that empty space is not truly empty. According to quantum field theory, the vacuum is a boiling sea of virtual particles constantly popping in and out of existence. These particle-antiparticle pairs normally appear for a fraction of a second, collide, and annihilate each other. They are the background static of reality, happening everywhere, all the time. But what happens when this quantum dance occurs right on the razor's edge of an event horizon? Imagine a pair of these virtual particles springing into existence precisely on that invisible boundary. The extreme gravitational gradient can pull one particle past the point of no return into the black hole. Meanwhile, its partner is left stranded on the outside without its twin to annihilate with. The trapped particle falls into the abyss, carrying negative energy according to the mathematics of the theory. The surviving particle, now real, escapes into the universe, carrying positive energy away. To an outside observer, it looks as though the black hole itself is glowing, emitting a faint trickle of radiation. This phenomenon is known today as Hawking radiation. Because the black hole is constantly absorbing negative energy, its total mass must slowly decrease. Yes, you heard that correctly. Black holes are slowly, agonizingly evaporating into the cold vacuum of space. This revelation bridges the gap between the colossal scale of gravity and the microscopic world of quantum mechanics. However, this evaporation process is unimaginably slow for a black hole of stellar mass. A black hole the mass of our Sun would take 10 followed by 67 years to completely evaporate. That is a time span vastly longer than the current age of our universe. For a supermassive black hole, like the one at the center of our galaxy, the timeline stretches even further. Long pause. It would take 10 followed by 100 zeros years, a googol of years, to finally vanish. But the implication is profound. Black holes are not forever. They are not the eternal victors of the cosmic struggle. As a black hole shrinks, its temperature rises, and the rate of its evaporation accelerates. In its final moments, millions of billions of years from now, it will not go out with a whimper. It will explode in a spectacular, blinding flash of high-energy gamma rays, returning all of its stolen mass and energy back to the universe in one final cosmic breath. But this incredible process introduces yet another terrifying question. What happens to the information? We previously discovered that information is painted holographically on the surface of the event horizon. Long pause. If the black hole evaporates completely and the event horizon shrinks and vanishes, where does the information go? Does it escape in the chaotic, scrambled radiation, or is it truly, permanently erased from reality? If information is erased, it violates a core pillar of quantum mechanics, which states that information must be conserved. This is the modern iteration of the black hole information paradox, a battleground for theoretical physicists today. Some physicists believe the Hawking radiation is not entirely random. They propose that it carries the encoded information out with it, subtly hidden in the quantum entanglements of the escaping particles. Others suggest the black hole never truly evaporates completely, leaving behind a microscopic remnant. A tiny, plank-sized crystal containing the compressed data of everything that ever fell inside. The truth remains one of the most sought-after prizes in modern science. To solve it, we will need a completely new framework of physics. We will need a theory of quantum gravity, a mathematical Rosetta Stone uniting Einstein's smooth geometry with the granular quantum world. This quest inevitably forces us to look inward, beyond the event horizon, toward the very center of the abyss. What actually lies at the heart of a black hole? According to the classical equations of general relativity, all matter that falls in is crushed into a singularity. A singularity is a point of zero volume and infinite density. It is a place where gravity becomes infinite, and the very concept of space and time ceases to exist. But infinity, in a physical equation, is usually a sign that our theory has broken down. It is nature's way of telling us that we are missing a crucial piece of the puzzle. Most physicists do not believe that true mathematical singularities exist in reality. They believe that long before matter reaches zero volume, quantum effects must take over. Perhaps at the center, matter is crushed into a Planck star, a hyperdense quantum core. Or perhaps the intense curvature of spacetime acts as a gateway to somewhere else. Some solutions to Einstein's equations suggest that a black hole could be connected to a white hole. A white hole is the mathematical opposite of a black hole, a region of space where nothing can enter, and matter is violently expelled. The tunnel connecting them is known as an E. Einstein-Rosen bridge, or more commonly, a wormhole. Could the matter falling into a black hole be funneled through a wormhole, emerging in a distant part of our universe? Or, even more staggeringly, could it emerge into a completely different, newly born universe? This gives rise to the cosmological natural selection theory. This gives rise to every time a black hole forms, a new universe is born on the other side of the singularity. Our own universe might simply be the interior of a massive black hole that exists in a much larger parent universe. This nested structure of realities would mean the cosmos is an infinite fractal of creation. It is a beautiful, intoxicating idea, though currently beyond the reach of our experimental testing. But it reminds us that our universe is likely far larger, stranger, and more interconnected than our senses reveal. Let us return to our own timeline, to the far, unimaginable future of our specific universe. Long after the last stars have exhausted their nuclear fuel and faded into dark cinders, long after the galaxies have been ripped apart by the accelerating expansion of dark energy, the universe will enter the black hole era. In this dark epoch, the only significant structures left will be the black holes. They will wander the empty, frozen cosmos, occasionally colliding in the dark to form even larger titans. But even this era will eventually come to an end. Trillions upon trillions of years from now, the slow process of Hawking radiation will dominate. The supermassive black holes will begin to shrink, shedding their mass photon by photon. The universe will be filled with a thin, impossibly cold haze of dying radiation. One by one, the great black holes will explode in final flashes of light, illuminating a dead cosmos. When the final black hole evaporates, the universe will enter its final stage, the dark era. The temperature will approach absolute zero, and all physical processes will grind to an eternal halt. Time itself will lose its meaning, as there will be no events left to measure it by. It is a bleak picture, the heat death of the universe. Yet, there is a profound serenity in this grand cosmic timeline. It forces us to appreciate the incredibly rare, vibrant window of time we currently inhabit. We live in the stelliferous era, the era of starlight, warmth, and complex chemistry. We are made of the ash of dead stars, gathered together by the gentle hand of gravity. It loves it. We are the universe's way of thinking, observing, and understanding its own magnificent mechanics. Every paradox we solve, every gravitational wave we detect, is a triumph of consciousness over the void. We are tiny, fragile beings clinging to a rock, yet our minds can stretch across billions of light years. Long power. We can visualize the crushing depths of a singularity and calculate the fading whispers of Hawking radiation. The study of black holes is not just about understanding distant, dark objects. It is about understanding the fundamental limits of reality, the absolute boundaries of space, time, and knowledge. They are the supreme laboratories of nature, where the universe tests its own laws to the breaking point. As we build better detectors, launch new telescopes, and refine our mathematics, we will peer closer to the edge. We may one day capture an image of the event horizon so clear that we can see the quantum jitter of space itself. We may finally decode the scrambled information hidden in the Hawking radiation. Until that day, the black hole remains the ultimate symbol of the unknown. It stands as a reminder that science is an unending journey, not a final destination. Every answer we find merely opens the door to 10 more profound questions. How did the supermassive black holes form so quickly in the early universe? Are there primordial black holes, tiny remnants from the Big Bang, hiding in our solar system? Could the dark matter that holds galaxies together actually be composed of trillions of these microscopic black holes? These questions will guide the next generation of astronomers, physicists, and dreamers. They will keep us looking up at the night sky, searching for the invisible forces that shape our destiny. The gravity that once seemed like a prison has proven to be our greatest tool for exploring the cosmos. It is the messenger that brings us news from the darkest corners of reality. It is the geometric canvas upon which the masterpiece of the universe is painted. As we close this epic exploration, take a moment to look at your hands. The atoms in your body are bound by the same physical laws that govern the crushing heart of a black hole. You are intimately connected to the grandest phenomena in the cosmos. You are a part of the grand geometry. When you feel the pull of gravity holding you to the earth, remember it is not a tether. This is the loving embrace of curved space-time, guiding you along your path through the universe. The paradox is broken, the mystery is illuminated, and the darkness is no longer something to fear. It is simply another landscape to explore. The universe is waiting, full of secrets, paradoxes, and wonders beyond imagination. Keep your eyes open, your mind curious, and your spirit bold, for the journey of discovery never truly ends. It merely changes its shape. Thank you for walking this path of shadows and light with us. The cosmos is a vast, beautiful place, and it is a privilege to witness it together. Continue to seek the truth, no matter how strange or counterintuitive it may seem. For it is in the strangest corners of physics that we find the deepest truths about our existence. Let the mystery of the event horizon inspire you to push beyond your own limits. Break free from the constraints of everyday thinking and dare to imagine the impossible. Because the impossible is precisely where the next great scientific revolution is hiding. The legacy of Einstein, Hawking, and countless others is now in your hands. It is up to you to keep the flame of curiosity burning bright in the darkness. So go out, look at the stars, and let your imagination soar. Remember that every point of light and every patch of dark has a story to tell, and we have only just begun to read the first few pages of the cosmic book. The greatest discoveries still lie ahead, waiting for a curious mind to uncover them. Perhaps that mind is yours. Until our next journey through the mysteries of science, may your nights be filled with wonder and your days with discovery. This has been a truly epic exploration of the most extreme objects in the universe. The dark heart of the cosmos has been illuminated by the power of human reason. We have stared into the abyss, and the abyss has shared its secrets. Thank you once again for being part of this incredible adventure. Farewell, fellow travelers of space-time. Keep exploring, keep wondering, and never lose your awe for the magnificent, beautifully complex universe we call home. As our journey tonight comes to an end, we have discovered that the great paradox that terrified physicists was not an error of the universe, but a flaw in our way of looking at it. Gravity doesn't need to escape from black holes for a simple and beautiful reason. It was never trapped in the first place. It is the indelible imprint on the fabric of space-time, the eternal and geometric scar left by a collapsing star. Left by a collapsing star. We have learned that the event horizon is not the ultimate abyss where everything is lost, but a perfect cosmic archive. A place where information freezes holographically at the edge of time. And thanks to the echoes captured by LIGO, today we know that these invisible titans are not lonely monsters, but dynamic dancers that collide and merge, making the very fabric of reality vibrate. It is profoundly poetic, isn't it? That the darkest, strangest, and seemingly most destructive objects in creation are, in reality, the ones that shed the most light on the fundamental laws of our cosmos. The next time you step outside and look up at the night sky, remember that the dark space between the stars is not an empty stage. It is alive. It bends, it stretches, it breathes, and it vibrates with the unbreakable gravity of stellar ghosts. Thank you for joining me on this journey beyond light, time, and everyday logic. If this exploration has challenged your mind and expanded your universe, I invite you to subscribe and leave your thoughts in the comments. Never stop questioning the obvious. Never stop wondering at the invisible. This was Nocturnal Science. Until the next adventure, and have a deep, serene, and inspiring night.